Thursday, October 23rd, 2025, AGNDD intelliReport topic, Redshift. Please pardon any visual and informational inaccuracies in this entirely AI-generated article-based video. Unlock the secrets of the universe. How astronomers use spectral analysis to measure cosmic motion through redshift and blueshift. Astronomers use telescopes and spectrometers to measure starlight intensity variations with frequency, comparing resulting spectra to lab gases like hydrogen. Redshift is determined by shifts in features such as absorption or emission lines. Redshift, Z greater than 0, or blueshift, Z less than 0, quantifies the relative difference in observed versus emitted wavelengths, lambda, or frequencies, F, where Z equals lambda observed minus lambda emitted, divided by lambda emitted, or Z equals F emitted minus F observed, divided by F observed. Doppler blueshifts indicate approaching objects, higher energy, redshifts receding ones, lower energy. Gravitational blueshifts occur from weaker to stronger fields, redshifts the reverse. The Doppler effect, explained by Christian Doppler in 1842 for sound waves and tested in 1845, was extended to light by Hippolyte Fizeau in 1848. William Huggins first measured stellar velocities via spectral shifts in 1868. Confirmations followed, including optical redshift in 1871 and lab verification in 1901. Vesto Slipher observed galactic redshifts from 1912, revealing recessional velocities. Edwin Hubble established galaxy distances in 1923 and formulated Hubble's law in 1929, linking redshift to distance. Theoretical models by de Sitter, Friedman, and Lemaitre supported an expanding universe by 1930. Redshifts measure differences in wavelengths between emitted and observed light, reflecting variations between source and observer locations. These are categorized into three types: Doppler shifts from relative motion, for example, approaching or receding objects; cosmological shifts from the universe's expansion, stretching wavelengths over vast distances; and gravitational shifts due to strong gravity fields, for example, near black holes bending light paths. Each type provides insights into cosmic dynamics. Doppler redshift occurs when a light source moves away from an observer, Z greater than 0, causing blueshift when approaching, Z less than 0, due to the Doppler effect on electromagnetic waves. For velocities much less than light speed, V much less than c, Z is approximately equal to V over c. Relativistically, for high speeds, 1 plus Z equals 1 plus V over c times gamma, incorporating the Lorentz factor for time dilation. This was confirmed in the 1938 Ives-Stilwell experiment. The relativistic correction is orientation-independent, unlike the classical component, which depends on line-of-sight projection. Cosmological redshift from distant galaxies is modeled in a homogeneous, isotropic universe using general relativity. It follows 1 plus Z equals a sub-zero divided by A of t, where A is the expanding scale factor, making Z positive and increasing with distance. In the Friedman-Robertson-Walker model, for large Z greater than omega sub-0 to the power of -1, the age t of Z approximately equals 2 divided by 3 times h sub-0 times the square root of omega sub-0 times Z to the power of -3/2, with omega sub-0 equals rho over rho critical and h sub-0 the Hubble constant. Redshift arises from accumulated Doppler shifts along light paths, not direct wavelength stretching. Precise calculations often require numerical tools available online. Galaxy redshift comprises cosmological expansion and peculiar motion components. The expansion-related redshift stretches light wavelengths as it travels through expanding space, unlike Doppler shifts from local velocity. Edward Harrison explains, light from a stationary galaxy reaches stationary observers after traversing expanding regions, stretching all wavelengths. Steven Weinberg notes this wavelength increase depends on the total growth of the universe's scale factor AT between emission and absorption, not rates at those instants. This model describes universal expansion distinctly from local motions. Gravitational redshift, or Einstein shift, occurs due to time dilation in a gravitational well. Light emitted inside appears redshifted outside, with fewer cycles per second. Derived from the Schwarzschild solution, the formula is 1 plus z equals 1 over the square root of 1 minus 2 gm over rc squared, where g is the gravitational constant, m the mass, r the radial coordinate, and c the speed of light. It stems from special relativity and the equivalence principle. Measurable on Earth via Mossbauer effect, Pound-Rebka experiment, it's infinite near black holes and influences cosmic microwave background fluctuations, Sachs-Wolf effect. Summary of redshift formulae. In special spacetime geometries, key redshift formulae are tabulated, highlighting that the redshift magnitude, z, is wavelength independent across all cases. This underscores a fundamental property in relativistic contexts, applicable to scenarios like gravitational, Doppler, or cosmological shifts. Astronomical redshifts are measured using distinctive atomic spectra calibrated in labs, showing consistent Z values for lines from the same object, attributed to Doppler-like effects rather than blurring. Spectroscopy is more precise but challenging than photometry, which estimates photometric redshifts with errors up to dZoxy 5 and allows qualitative assessment, for example, sun-like spectrum at Z equals sin 1 peaks in infrared. Reliable redshifts require known rest frame spectral lines. Unidentified or featureless spectra like gamma-ray bursts are unsuitable without optical afterglow analysis. In the Milky Way, observed redshifts and blue shifts primarily indicate line-of-sight velocities, enabling measurements of stellar velocities and masses in spectroscopic binaries. They aid in detecting exoplanets, determining orbital parameters via transits, and tracking multiple objects. Finely detailed redshifts support helioseismology for solar photosphere analysis. Applications include measuring planetary rotations, interstellar cloud velocities, galaxy rotations, and accretion dynamics onto neutron stars' black holes, incorporating Doppler and gravitational effects. Doppler broadening reveals temperatures, while 21 cm hydrogen line shifts map interstellar gas velocities and galactic rotation curves as seen in the Milky Way and Andromeda. Redshift measures cosmic expansion. Distant objects show larger redshifts with the cosmic microwave background at Z equals sin 1089, dating to 13.8 billion years ago. Quasars were the first high redshift discoveries. Hubble's law links redshift to distance for nearby galaxies, aiding crude distance estimates. Peculiar velocities from gravitational interactions cause scatter, enabling probes of cosmic structure. The law assumes constant expansion, but it's nonlinear for distant objects, revealing the universe's history. Observations of type Ia supernovae indicate recent acceleration in expansion. The highest confirmed spectroscopic redshift is for galaxy JADES GSZ 14-0 at Z equals sin 14.32, 290 million years post-Big Bang, surpassing GNZ 11's Z equals sin 11. 1. Lyman break records include A1689ZD1 at Z equals sin 7. 5. Distant objects, GRB 090423 on Z equals sin 8. 2. Quasar Ulysses J1342 plus 0928 Z equals sin 7.54. Radio Galaxy TGSS 1530 Z equals sin 5.72. And molecular emission in SDSS J1148 plus 5251, Z equals sin 6.42. Extremely red objects, EROs, and hyper-EROs, HEROs, may indicate high redshift galaxies. CMB is at Z equals sin 1089. Evidence suggests population 3 stars in CR7 galaxy at Z equals sin 6.60, aiding early element formation. Predicted events include neutrinos, Z 10 circumflex 10, and gravitational waves, Z 10 circumflex 25. Advancements in automated telescopes and spectroscopes have enabled redshift surveys to map the 3D distribution of matter in the universe by combining redshift with angular positions. These reveal large-scale structures like the Great Wall, a supercluster over 500 million light-years wide. Key surveys include CFA Redshift Survey, 1977 to 1982, the first, 2DF Galaxy Redshift Survey, completed 2002, measuring 220,000 galaxies, Sloan Digital Sky Survey, SDSS 1998 to 2023, with redshifts up to 0.8 and over 100,000 quasars at z=3+. Deep 2, Keck telescopes, ended 2013, recording 38,000 objects at z=0.7+. Radiative transfer and physical optics can cause wavelength and frequency shifts in electromagnetic radiation via energy transfers to matter or photons, not frame transformations. These include coherence effects or scattering from particles, particulates, or refractive index fluctuations, for example, radio whistlers. In astrophysics, such shifts are termed reddening rather than redshifting, which is reserved for relativistic effects. Scattering often reddens radiation due to entropy favoring low-energy photons with wavelength-dependent Z and angular variations. Multiple scattering distorts lines. Interstellar reddening reddens spectra without shifting lines, causing dimming and distortion, distinct from atmospheric Rayleigh scattering, for example, sunsets. Blue shift, the opposite of redshift, occurs when an electromagnetic wave's wavelength decreases, boosting its energy and frequency. In visible light, this shift moves colors toward the blue spectrum end. Doppler blue shift occurs when a source moves toward an observer, shortening wavelengths and increasing frequencies of light or other waves. It's visible as bluer hues only at near relativistic speeds, but applies broadly. In astronomy, it's key for measuring relative motion. The Andromeda Galaxy blue shifts toward the Milky Way. Binary star components blue shift when approaching Earth. Spiral galaxies show blue shift on nearing sides. Blazars emit blue shifted radiation from relativistic jets. Stars like Barnard's exhibit minor blue shifts. It helps isolate motion from cosmological redshift in distant high Z objects. Gravitational blue shift is absolute, unlike angle-dependent Doppler blue shift. Photons gain energy, blue shift, falling into a gravitational field and lose energy, redshift, climbing out, depending solely on radial distance in the potential well, not emission or reception angles. This stems from energy conservation and mass energy equivalence, verified by the 1959 Pound-Rebka experiment. It affects cosmic microwave background anisotropy through the Sachs-Wolf effect, where evolving gravitational wells cause mismatched blue shift on approach and redshift on exit for passing photons. Faraway active galaxies, known as blue outliers, exhibit blue shifts in their O3 emission lines, indicating motion toward us. A prime example is the narrow-line quasar PG 1543+489, with one of the largest blue shifts at a relative velocity of 1150 kms. In a hypothetical Big Crunch scenario where the universe contracts rapidly, distant galaxies would exhibit increasing blue shift, light wavelengths shortening as objects approach. This reverses the real universe's redshift seen in expansion, where farther galaxies appear more redshifted due to stretching wavelengths. Summary of recommended readings in English. Odenwald and Feenberg's 1993 article in Sky and Telescope, February 2003, paper 3135, explores the three types of galaxy redshifts, Doppler, gravitational, and cosmological, and their distinct causes, aiding in differentiation. Lineweaver and Davis's Misconceptions About the Big Bang, Scientific American, March 2005, demystifies cosmological redshift, explaining space expansion physics while addressing common myths about the universe's evolution. This bibliography lists key textbooks on cosmology, astrophysics, general relativity, and the expanding universe. Highlights include Nussbaumer and Bieri's Discovering the Expanding Universe, 2009, Binney and Merrifield's Galactic Astronomy, 1998, Carroll and Ostley's An Introduction to Modern Astrophysics, 1996, Feynman's Lectures on Physics, 1989, Misner, Thorne, and Wheeler's Gravitation, 1973, and Weinberg's Gravitation and Cosmology, 1971. For applications of cosmological and gravitational redshifts, refer to physical cosmology textbooks. Thus, Redshift continues to unveil the universe's expansion, bridging historical discoveries to modern cosmology's profound insights.
Thank you for watching this AGNDD intelliReport, dear viewers. Please like, subscribe, and click the bell button to get notified during new uploads. And make sure to tune in next time. Stay safe and healthy. Cheers!